Good afternoon, ladies and gentlemen. Welcome to Hong Kong IS Distinguished Lecture Series. I'm Jacob Huang, the Executive Director of Hong Kong IS. And today we are very happy and honored to invite our Vice President of Research and Technology, Professor Jian Li, to give a Hong Kong IS Distinguished Lectures. Professor Jian Li is a chair professor in Mechanical Engineering Department in CDU, and his primary research interests advanced narrow materials and its integration in mechanical and biomedical system by using the combination of experimental mechanics and mechanical simulation. He has also branched out into several other interesting areas, including surface science and engineering, biomechanics, residual stress, and narrow mechanics. And he has published more than 360 SCI top journals, including papers in Nature, Science, Nature Material, Nature Communication, Science Advanced Materials Today, Advanced Materials, PRL, Additive Material, Journal of Mechanics, and Physics of Solid, etc. And Professor Jian Li has received the French Knight of National Order of Merit and French Knight of the National Order of Legion d'Honneur in 2006 and 2017, respectively. He has elected as a member of National Academy of Technology of France in 2011. Also, Professor Jian Li received the Guanghua Engineering Science and Technology Award from the Chinese National Academy of Engineering in 2018. He has also been elected as a member, a fellow of Hong Kong Institute of Science in 2013, and also he's a senior fellow of Hong Kong IS. So we are really honored to have you to give a lecture on the progress in additive manufacturing from 2D printing to 4D printing of structural materials and functional device. So let's give a warm hands to Professor Jian Li.
Thank you, Professor Huang, for this very kind introduction. So it's my great pleasure to present our recent work on the 2D printing, 3D printing, and 4D printing. So this is the outline of my presentation today. So I will talk about what is 3D printing, 2D printing, and 4D printing, and also I will present our recent work on the super nanostructured material. And then I will introduce the 3D, 4D printing of nanomaterials and application and future development, and some conclusion and future remarks. So additive manufacturing is one of the key tools for the advanced mobility solution. So as you all know, the structural material, in addition of the civil engineering, is a main application field is mechanical engineering. So we always try to find a higher efficiency mechanical system, such as marine system, space, aircraft, car, and high-speed train, and also all the mechanical or moving parts, such as smartphone. Today is a very important element in our daily life, but also it's very important to have a lightweight solution for smartphone, to add more chips in our smartphone, or more battery in our smartphone. So the major challenge for the structural material, basically we need to solve is how to manage the strength and the ductility, these two conflicting properties. So as we all know, quite often when we increase the strength of a material, then the ductility drop. So with additive manufacturing, quite often we can solve the problem because we can produce a component and a structure with tailor-made property. There they need strength or where they need ductility. So I would like to introduce first a little about the activity of the research center for which I worked. So basically, when I joined CTU, I created this Center for Advanced Structural Material. So today we have different faculty members, but we mainly work on the multi-scale mechanics of advanced material. So the object we study or material we study are high entropy alloy, intermetallics, and metallic glass. So we have our expert Professor C.T. Liu here. And also, personally, I mainly work on the structural nanomaterial, super nanomaterial, and 3D printing. Of course, we also work on some generic tools such as material genome and 1D, 2D material mechanics. So these are the major activities in this research center with 7 active faculty members who are core members of this center, but also another 6, 7 faculty members who join this as a normal member. So what's the major problem for the structural material and for the material of future? So I recommend you to go through this interesting book. One of the authors is here, so Professor David Strovich. I saw your name here. So most importantly, the material for which I work, I will present here, metallic material are quite so-called old function material. However, how to generate new study in this so-called old metal, then this book indicates 3 major directions. One is a fundamental study of classic metal and alloys. The second one is high entropy alloy. The third one is nanostructural metallic material. So I think what I will present is mainly in the 3.13, and also in the ceramics and the glass. Of course, what's the application? That can be material for energy, catalysis, and etc. So when we create a material, as I said, the ideal case is to develop a tailor-made material where we need the strength, then we try to reinforce locally the strength. Where we need geometry, we try to generate that geometry. So if we go down to the atomic level, basically what we try to do in the material science, and particularly in the structural material is how to generate or how to manage the heterogeneity in this material. Okay? The 3D, 2D, 4D printing allow us to generate all this kind of heterogeneity because it's possible to use additive manufacturing to create a totally new material by combining different type of material with different properties. But generally speaking, we have chemical heterogeneity and topological heterogeneity and physical heterogeneity. Okay? So what we know in the past in the material science, particularly for the metallic material, so we can generate precipitate, and with nanotechnology we generate precipitate at the nano level. Another issue is multi-phase, ground boundary, twin boundary. Okay. Then if we go down to another scale at the atomic level, so we have we can generate composition fluctuation, okay, such as high entropy alloy. So we can easily generate this kind of distortion, and also we have lattice distortion. So when you insert different material with different atomic size, then locally you generate a lattice distortion for a normal structural material. Of course, we can also have other defects such as vacancy, pores, dislocation, phase boundary. All these can be managed. So we can say today with different tool, manufacturing tool, material processing tool, we can try to manage and organize all this for the final objective of optimized material component and devices and structure. So basically, for the material I will talk today, we mainly start from different type of materials. We can call it nanostructural engineering. So we can start with a material like a metallic glass, so without any order inside of the structure. Then if you partially organize the order, so you may have a nano crystal with glass. In this side, if you generate ground boundary stabilization, we can generate locally heterogeneity and also high hierarchical nanotwin is another type of the nanostructure. We can manage to have high strength, high ductility, and of course, generally speaking, we can say it's a dislocation engineering, how to manage the dislocation inside of a small domain. This domain can be created by the 2D, 3D, 4D painting. So everybody talk about 3D painting, 4D painting, how it's become a very hot topic. So how hot is this? So if we go to see the sensitization index, so we can see in 8 years, the publication has been increased by 18.5 times. Okay, I take other so-called hot topic like battery, perovskite material 4 times. Nano is already quite mature, so in 8 years, only say less than 200% increase. So for the even in 2 years, it's accelerate, as you can see here. Okay, so additive manufacturing, 3D, 4D printing have been increased roughly double in 2 years publication. So I take another very hot topic, CRISPR is in biology. In 2 years, it's only 161%. So why this field is so hot? Because that give material scientist and mechanical engineer and designer to have the possibility to create totally new material with different way to say put the material together. Okay, so for this reason, it's become a very hot material and process. Of course, we generate say tons of methodology to put the material together. For this reason, it's not like other field. We have not yet focused on some particular process. Okay, although every month there's a totally new technique developed for the creation of another type of material, but it's a very interesting area and an interesting period for the young people because when you start some process, then it's interesting to work in. But additive manufacturing actually is quite old. So personally, I don't talk about the coating, welding, all these kind of process which are very close to today's so-called additive manufacturing because I work on the residual stress, as Professor Huang said, for more than 35 years. So starting from day one, I work on the layered welding for nuclear plant preparation. But the first time when we really call it rapid prototyping is in the 19th. Okay? In 19th, we have developed different photoelasticity technique to produce the 3D structure and try to generate photoelasticity and to better understand the stress applied on a complex mechanical system. So at that moment, we use the so-called stereolithography. So it's a polymerization with ultraviolet light. Then we can polymerize locally, point by point, and then we build the 3D structure. And that technique was used largely in automotive, aerospace industry for checking the stress. Okay, so it's just rapid prototyping to validate the design concept. But today it's totally changed. This is the photo I took last year in Frankfurt, so in the largest exhibition for the additive manufacturing. Okay, we organized a Sino-German workshop there. At the same time, I visited the floor. So as you can see today, how complex the real metallic structure can be produced. So this is say one-piece turbine structure. Okay, that can be produced by additive manufacturing. So tomorrow, many colleagues here are working on high entropy alloy. We can easily imagine we can have for each stage of the blade is a different material. Okay, so we can imagine we can have titanium alloy, nickel-based alloy, ceramics, and everything together. Then you have a huge machine which can produce these together. So this is a machine produced by one additive manufacturing machine. So that means the technology is progressing a lot. So for this reason, we are also working on this field. 25 years after I studied the stereolithography for rapid prototyping. Okay, and also, of course, I always study the residual stress for more than 35 years. So I feel now I'm in the right ground for my research. Okay, so what's the future development of 3D, 4D printing? In my view, the most important thing is the ink or powder design, because this is the basic element to build the structure. It's a brick of the brick can be at a nanometer level or larger level, okay? But this is the very important element. Then the printer design. Of course, the machine is different than classic tooling machine or other machine for machining the structure. And of course, it's possible to develop the material itself, which is, to me, is a phase engineering. And of course, we need to have a press stress engineering to manipulate, because when you put different type of material together, due to the difference of thermal expansion coefficient, you have a totally different stress inside of the structure. Because before, when you cast a structure, and when you're forging a structure, the gradient is not so high in terms of composition and in terms of stress. Okay, so what we can achieve if we are able to produce this? First of all, I think in future we will have more and more soft material combined with a hard material. Okay, as I said, sometimes we need a strong material and sometimes we need ductile material, but it's very difficult today to put together, and with additive manufacturing it's possible to put very soft material with very hard material. Then with 4D and plus printing, we will be able to develop integrated solution, and also with artificial intelligence, we can generate functionalization. So all the new system will be changed. That not only change the manufacturing process, but that will change the whole life, because not only we can produce mechanical structure, but we can also produce soft structure. So I will show you some soft structure produced by 4D printing. So now I move to the super nano structure material. So I call it 2D additive manufacturing. So the example I show you is metallic glass combined with a very small nanocrystal. So why we have this idea? So in 10 years ago, basically by the simulation, we observe if we can mix two material at atomic level, okay, with the same composition, say, with only 20% mechanical properties difference, we can generate a so-called multiple shear band failure mechanism. Because for the metallic glass, it's like the normal glass. When you have initiation of failure, it's very difficult to stop. But if we are able to generate a structure that naturally generate a multi-shear band structure, then we can solve the problem. Then we try to use the heat treatment to generate a material mixed with glass and nanocrystal, but it's very difficult because thermal heat treatment is not easy to manage because at the atomic level. So for this reason, we only observe some change and some mixture, but it's very difficult to put it, say, homogeneously across a volume. Then we try to better understand the material with their heterogeneity. So we develop a dynamic micropillar test and also a fast beta relaxation to better understand the relationship between the heterogeneity at atomic level with mechanical property, especially the, say, shear band initiation. Okay? Then it's quite difficult, and then we switch to a new type of material, which are super nano structure. So at beginning, we try to produce this super nano structure with two metallic glass mixture. Okay, so we try to obtain two metallic glass or a material with nanocrystal and metallic glass. But it's quite difficult to produce this because when you have two material with same composition, it's very difficult because either that become nanocrystal, either that remain metallic glass. Then we design a process, we observe if we can manage the composition properly, we can obtain this structure. So the blue part, as you may see, the atom is aligned with a regular manner, and this crystal. The size of crystal is only 6 nanometer. Then the yellow part, metallic glass. Okay, so we have successfully obtained this structure, and surprisingly, the mechanical property in terms of strength, deformation capacity is much higher than the magnesium-based alloy, and even much higher than the magnesium-based metallic glass, reputed to be very strong compared to the material. So then we try to understand what's happened in this particular material. And this is one kind of additive manufacturing because we have a substrate, we have this is a PVD, quite classic PVD. The main importance is how to design the substrate. During the PVD process, what we have successfully obtained is the phase separation. After phase separation, we have a material with a crystal, and another remaining part is metallic glass. So why, as you may see here, this structure is very nice. We have a crystal distribute regularly, and metallic glass, amorphous material, also distribute regularly. If we do the chemical composition analysis, we can see at the center of, in this crystal, we have a material with copper-rich crystal, and outside is magnesium-rich amorphous material. So basically, we need to have two material, and during the processing, we have a phase separation, and two phases are distributed equally and homogeneously inside of the structure. Then compared to the theoretical limit of the material, which is Young's modulus divided by 20, you can see the newly created material is very close to the new theoretical limit. And before our study, you can see the largest sample, which are close to the theoretical limit, are 8 nano, 75 nano, and 220 nano. And here it's still small, but it's 1.3 micrometer. So what's the application of this kind of, I just show you one example of the orthopedic implant. So with the aging problem in the world, we have more than more fracture, and every 3 seconds we have one hip fracture in the world. Okay, when the average age increase, then the problem comes to all the patients. So the problem is when you have a bioimplant, then today we mainly use titanium as a material or stainless steel. But you may need another operation to, for example, if you have a fixation of the bone, then you need another operation to extract the material. So the ideal case is to develop a biodegradable material. Magnesium is a very good candidate to this, but the only problem is the strength. It's very weak material. So how to have very strong material so we can combine the pure magnesium or magnesium alloy with this, say, additive manufacturing 2D added structure that can drastically already increase the strength of the material. So you can see here, we use this is the base material. It's already a very strong alloy. And if we use the surface mechanical attrition to generate the nanomaterial plus this coating, then we have roughly double the yield stress without sacrifice any deformation capacity. This is a gradient structure, and then we have excellent biocompatibility and strength of the material. So for this kind of combination, we are doing a large animal test. So I hope very soon that will be on the human test and the market for the biodegradable implant. In terms of strength, it's roughly 10 times of base alloy, and wear resistance increased by 50% because this particular structure, the friction coefficient has been drastically reduced. So another example of this kind of technology, today the smartphone is a very popular say application. So here is one example of this. You can see we can coat the structure with an optical coating with different color. But more importantly, this substrate is a polymer substrate. So tomorrow we can imagine a soft smartphone and roll together. As you may see here, it can be rolled easily. And how to have a very deformable structure. So this is one example. It's an aluminum-based alloy using the similar technology. You can see here the deformation capacity is very high for this aluminum. So how that happened? Basically, we have, you can see during the deformation, compression, and tensile test, this material is very ductile. Why? Compared to the previous material, the grain size is smaller than 10 nano, so without any dislocation. Here is 10, 20 nano, then the grain has a capacity to deform. So for this reason, this material has a very strong strength, but with high deformation capacity. Okay, so you can see here, when you do the compression test, we never see the crack. So from here and with a very high deformation capacity. So now I move to the 3D, 4D additive manufacturing of nanomaterial. Okay, so basically we work on our roadmap is to work on 3D printing plus nanomaterial. The sector for which we work is high added value sector, which are aerospace, space, and biomedical. So basically, we try to develop new super nano alloy, as I described before, and because right now we can produce up to 50 to 100 micron thick this coating. Okay, the paper we show you is around 10 micron, but with process development, we are able to produce, for example, for 1 millimeter thick sheet, we can add it 50 micron in each side of the material, so that is a quasi 3D structure, okay? Especially for aerospace or other lightweight solution. And also, we develop the new processing for ink and associate sintering process after 3D printing. Of course, we have 3D, 4D printing plus. I will show you what is this. And also in situ densification using the surface mechanical attrition for enhance the fatigue property of the 3D printing of metallic material and also the new integration. So what is the 4D printing? Okay, so basically the 4D printing concept can be used for all type of material. That can be metallic material, ceramic material, and polymer material. So basically we can use, for the metal, we can use shape memory alloy, or elastomer derived ceramics, or shape memory polymer, hydrogel, all kind of material. And why we call it 4D? Basically you can print in 3D structure, okay? The structure is always 3D. Why is it 4D? 4D means we can edit a multi-stimuli driven morphing, okay? You can change the shape. If you edit a light, if you heat, if you edit a magnetic field, if you edit a liquid, I will show you some example. Electricity, press, gas pressure. So you design something with a programmable structure, then you can obtain another shape than the initially printed structure. So for this reason, we can say it's a 4D, okay? Of course, I don't say if you combine this, that becomes 5D, if you combine, so, okay? So basically 4D means 3D structure added one stimulus or multiple stimulus, okay? You can modify it with a programmable manner, okay? So basically, if we come to the ceramics, so basically it's a 3D printing plus programmable self-shaping. So self-shaping means when you print something during the sintering, the material becomes like this. Okay, at the beginning it's flat due to the heterogeneity, anisotropy designed, embedded in the structure, then you have the final structure like this. So this work has been widely reported in China, in the United States, or even in Russia. Okay. So basically, the first 4D printing ceramics is we print a structure, and then we have a structure that can fix the shape. Then we do the sintering of the structure. And this is a primary, say, ceramic origami structure with a press-trained precursor. So these are different systems we use. So with material preparation, 3D printing, furnace, then we can we edit the biaxial stretch device. Then we can print this structure on this press-trained device. Then when we relax this press stress, then the structure can become very complex. So basically, we have designed a super elastic precursor that can be deformed very easily. So you can see if I only do the sintering of a part of this structure, I can have a half soft like this and half hard material, okay? So the material obtained is also a dual phase material with a nanoparticle crystal with 20, 30 nanometer and also amorphous matrix plus nanometer pore. So nanometer pore can probably use also for catalysis because the catalysis so can go to this nanopore and then we can imagine we can print a structure. So how complex the structure can be. This is an example of the, we print the precursor as a sheet, then we deform this and we sintering, then we obtain this complex shape that cannot be obtained by a normal 3D printing structure. It's origami, and if we deform the substrate, we print this structure on this substrate. If we deform in that direction, then after sintering is this shape. If we deform like in y-axis is like this, it's a basically symmetry of this, but if we combine with any angle, so you can imagine we can obtain very complex structure. So this is one example to how to develop a 4D printing structure. So basically, we print a structure with articulation point. You can see here, okay? Then we print this structure on top of a substrate, and this substrate is deformed during the printing, okay? You can see here, during the printing, then when you relax this, so we deform, okay? Then we print on top of this. So as you may see, if it's a bi-axis, we can generate many types. When you relax this, then you can obtain many combinations of the structure. So for the ceramics. But how about the mechanical property? So this mechanical property, sorry, is in Chinese and English. Okay, so you can see here our mechanical property is quite good, especially compared to the 3D printed ceramics. So for the same strength, specific strength, our size is 1 to 3 order larger. We can even print even larger structure. Okay. So basically, the 4D printing ceramics, we can print a multi-layer system with press stress. Then during the self-assembly, during the this is by simulation, but the reality also is the same. And also we can print a structure, and then with after this structure is can have the shape as we want if we anticipate to have a different type of articulation point. Okay. So what's the application for this development? Okay. So the advantage of this 4D printing, say, is we can say basically print all kind of complex shape of the ceramics. So that may be interesting for the chemical engineer, because tomorrow if you want to put your catalysis in many structure, then it's possible. You have plenty of choice. Of course, here we have hard material, which are ceramics, but we can imagine we can also print a soft material when that takes the shape, that can take any type of shape. Of course, another application is for 5G, because as you know, the case in the past is a plastic polymer material, and today is mainly metallic material, and tomorrow for 5G with metallic material, the electrical signal will be shielded by the structure. So we are looking for a new case for the future generation. Either it's a polymer, so we come back to Nokia solution, either it's a ceramics or glass. Glass, the weight is quite high. Then the ceramics, the challenge is how to build ceramics with different shape, and also how to build a flexible system. You know, today the screen is a flexible screen, so we can imagine we have a hard part in ceramics. In between is a soft ceramics with super elasticity, so we can easily deform, and these ceramics should also be quite strong, because the mechanical property should be quite good, should be at least better than glass. Otherwise, glass may be better solution. But today, there are many competition between ceramics and glass. There are also people work on the price-stressed glass, okay, with a thickness of say less than 100 micrometer, okay. So these two materials will compete, but as I said, we can also print glass, okay. So this is the same generic solution, and tomorrow we can have different shape if we print the structure with different anisotropy and heterogeneity, and after sintering that take the shape we want. Okay. Then another application is thermal barrier coating, okay, or directly print 3D ceramic turbine blade. Okay, so as I said, I show you a small engine directly print by 3D printing. But in future, we can imagine all these stages print together with a huge machine. Parts will be ceramics and parts will be metallic material. So why we need thermal barrier coating? As you see, so we have Professor C.T. Liu work on the super alloy. So in more than 50 years, 55 years, we basically increase the working temperature by 150 degrees, okay? So it's a very small progress, but if we coat the structure, so then the working temperature can be increased by 200 degrees. Then if we have a smart cooling solution, then the working temperature can further be increased by another 200 degrees. But today, to produce a material, a structure with a very good complex shape in ceramics is very difficult. But our solution, I think, in future, it will be possible. So we try to do something. So you can see we can have a very complex structure. And today, this is 2 years ago work, but our new work has not been published. But today we can have a 10 micron precision for this structure. And this structure is very highly resistant for high temperature shock. So we do believe in future we may have a very complex shape in high temperature resistant ceramic structure. And also we can have some structure on the space. You know, the space, the temperature gradient is very high. When you are faced to the sun, the temperature is very high. The other side is very cold. So how to develop a system that resists this kind of thermal shock is also possible with 3D or 4D printing structure. So we can imagine we can bring our structure on the space and produce whatever we want for either for thermal shock resistance or for other things. And also we can have lightweight amorphous ceramics, and also for any high temperature applications. And another application is the shielding of the neutron. So I see Professor Kai and all the colleagues. So today, on the space, we have a lot of radiation of cosmic ray. Okay, cosmic ray can damage the structure of the space shuttle, but also can damage the people. So if tomorrow we can produce a very light structure with the capacity to absorb the neutron, then we may say extend the life of the space shuttle or less damage the astronaut. So these are, of course, we can also use this kind of technology for nuclear plant, but in the nuclear plant, we don't need the so complex geometry, and we don't have a requirement such as lightweight structure. But in the space, every kilogram saved is around 100,000 US dollar. Okay, so if you can save 10 kilogram to do the same thing, then you can save a lot of money and have a more so-called working load for the other mission. So what's the next? So the next is, as I said, what's the stimulus? What I have shown you is the stimulus due to the heterogeneity of different layers. But this, can I have this? This one is with a magnet. So with magnet, you can generate any shape of the, say, geometry difference. And we also use this technology to press stress or enhance the mechanical property of 3D printed structure. The major problem of 3D printed structure today is the fatigue life, because due to the heterogeneity of the temperature during the laser sintering or other type of high energy sintering, then you have heterogeneity. It's very difficult to control. But use this homogenization technique, we can have a structure, use the surface mechanical attrition, and we have done on the fatigue sample, and we will see so the sample with a well-designed, smarted area to achieve desired strength. Okay, so this is to show the feasibility of this structure. So we 3D print the fatigue sample with HIP treatment. We densify the material and we prepare the fatigue sample, and then we treat this fatigue sample using this technology, and then you can see, compared to the as-built, so normal 3D printing, the fatigue strength is only, say, 280 MPa, and then after, if we use HIP, it's here, a little bit better, okay? But if we use HIP plus SMART, you can see we can roughly double the fatigue resistance. So this fatigue resistance is very close to the forging titanium alloy. So that means tomorrow we can have a very complex structure with very high fatigue strength, similar than the other technology, but with much more complex structure. And so this is another example we can do. So this is a direct return shape morphing structure with rapid and programmable multiple motion. So here we put this structure in the water. Is that become a 3D shape, and then we put it in alcohol, then it's become flat. Okay, so the technology we develop is a very fast transformation. This is another example. Can I have the movie, please? So basically, we can, so again, it's we put in the alcohol, that's become flat. Then, so you can see here, this flow. So we can design with different speed of deformation. Then we can have whatever the shape you want to design. And here, we combine this ability to build a structure. So we call a programmable multi-motion, okay? Because the motion of each component is different. Okay, so we design this without anything. It's a flat structure. Then we put in water. Then that become red fish. with complex structure. Okay. Of course, if we put it on alcohol, then that become flat. So what others? So another example, we can print embedded different material inside. Then this example is a simultaneous change in color, brightness, and shape. Okay, so then we can. Well, that take quite a long time in this particular case. That take more than 10 hours to change. As you see, the previous solution can change the shape very quickly, really in time. But this one is to show it's possible to change the color, brightness, and shape. It's just to give you one example of the 4D printing, because with a programmable manner, tomorrow we can build whatever the shape, whatever the property. We can build something sensitive to the light, to other energetic stimulus, and then change the shape to go to the programmed shape you want at the beginning. So this is very important. It's not any shape. So this is and the same. So we can embed it, the active layer, passive layer, a different layer. Then we can say obtain the shape you want by the design. So to conclude, the additive manufacturing is a very powerful tool for the development of new design due to its tailor-made solution nature. So this is very important. Tomorrow, if you don't care about the cost, basically we can tailor-made many things. Of course, we try to tailor-made artificial heart, artificial liver, but we are still working now on this. But the question is how to solve the tailor-made solution. So the 2D additive manufacturing of super nano structure material can provide lightweight solution for many space component, aerospace structure in magnesium, aluminum, and titanium. Okay, so now we work on the, for example, for the titanium and aluminum, the mechanical property is much better, even with 10 micron, 50 micron coating. Then 2D additive manufacturing can produce the super light and flexible device. As I show you, if we coat it on the polymer, at the beginning it's a very stretchable structure, but we enhance the Young's modulus of all the structure. Then the 2D additive manufacturing can produce component with very low friction coefficient. Okay, so I show here, I call 2D because the added part is 2D, but the component is actually also 3D. Okay, then the 3D, 4D painting of ultralight ceramic precursor and complex shape ceramics will allow the fabrication of heat and thermal shock resistant and radiation resistant material in the space, or even for the aerospace industry. The technology, because if you take a flight every day for a very long time, you are also sick. So I don't know if it's a direct link with radiation, but I know that may be a problem. So the technology can also extend to other high melting temperature material. Okay, we show the ceramics, but we can also do other high temperature material with complex shape. Okay, like tungsten or other material. So the fatigue resistance of nanostructured 3D printing titanium is 2 times of the as printed counterpart and offer additional rooms for weight reduction for the reused structure. For example, aircraft, and even for the space application. As you know, Tesla, for Elon Musk, SpaceX developed a technology to reuse the space shuttle. And in this case, fatigue is an important parameter. Before, you only launch one time, then it's not a problem. The newly developed technology can incorporate other mode of 4D control, such as magnetic, water, alcohol, light, heat, thermal property gradient. So anything you can incorporate in the structure. So that open the boulevard for the creation of new material. Okay, any new material you can use the 3D printing, and the machine becomes cheaper and cheaper. So one of the company in Shenzhen, they collaborate with us. How many 3D printing machines they sell? 2 million. Okay, worldwide. Okay, so the machine cost is like our color printer. It's a 2,000 3D printing machine today. Okay, so with this, I would like to thank all the funder, National Science Foundation, Ministry of Science, Technology, and also different industrial partner. This is my group who has contributed to this work. Thank you very much. I'm open for questions. Thank you.
Thank you, Professor Jian. Excellent talk. So I think we still have about half an hour for Q&A section. So I think, any question from the audience first?
The first one, you said you print the ceramics precursor, right? So what is precursor?
Yeah.
Is it ceramics or just some form of materials mixed with ceramics? The first one.
Yeah.
The second question is related to fundamental understanding of the 4D printing morph structures. Now, essentially, it's a string engineering. Use real strings to create new structures out after printing. But we know that once the structure, after morphing, you develop stress inside the structure, which means that the energy of the system increases. You do need a mechanism to lock in this morphed structures because essentially, energetically, they are more higher than unmorphed structures, right? So what about if the material will relax stress with the time? So the morphed structure with the time will change the structure ultimately, as you showed us, okay? So,
okay.
So the ceramics, what's the
okay, so first question. The ceramics, so we have a precursor, polymer precursor, okay? We mixed with ceramics. Then after the sintering, in fact, the polymer become, some part burning, and other remaining part become silicon oxide carbide. It's another amorphous ceramic. So it's a composite of ceramics with nanopowder. So in this particular case, it's a zirconium oxide.
So you heat it up after printing. You heat it up.
Yeah, after printing, after printing to some certain shape, then we heat up.
I see.
After sintering, that takes the shape you have seen
I
here.
see. Thank you.
Then the second question was on
I think the second question related to how you can keep the shape. Because if you don't heat it up,
yeah,
you have stress developing the structure, right? And the stress will raise the energy.
yeah,
So now, naturally, the system will relax to a lower energy state by release the stress. After release stress, the shape will disappear. So without the sintering, I think
okay.
people will.
Without sintering, we cannot obtain this shape for very long time, but we can edit other type of stimulus, okay? Like I have shown, water with alcohol, light, everything can change the form. So basically, if you have injection of energy, that can change the shape, okay? Then this injection of energy can be any times, any material or any matter, okay? If you inject additional energy, that changes the shape.
Okay, thank you.
Okay. Can we have one question from France, from our ISC fellow, Professor Solasson? So he asks, first he says, wonderful lecture. What about the recyclability of integrated materials?
Okay. In fact, the material, if the material is, for example, biodegradable, like magnesium alloy, then itself is you can recycle. Okay, so it depends which kind of material you print in. Of course, you can print a biodegradable material or other material that can be burned or the other can be treated. Okay, like aluminum, you can recycle many times of this material. So it depends on the design. Of course, from time to time in your design, you cannot skip some material that cannot be recycled. So this is a design problem to me. Of course, to reach some performance objective, from time to time, we may need to use material which has a very lower recyclability of material. But if the design pay attention, I think the recycle issue can be, say, solved or minimized. Okay. And another question?
Maybe we can, one question from the audience. Yeah. Yes, Professor.
Yeah.
Can we control the structure of the amorphous materials, such as the middle range ordering or the short range ordering, by using 3D printing?
Yeah, I think we can, because with basically when I talk about 2D, 2D is a question of time. Okay, 2D can easily become 3D. Okay. In this super nano technology, then it's quite easy to produce any material from glass to crystal mixture. Okay, so any combination. For example, we are working on some magnetic structure. Okay, then we don't know which composition can give us the best combination. Then we do something like material genome, okay, high throughput testing. So we have different combination of process. Then we have say 50% crystal, 40% crystal. So I think it's possible. We just need to well tailor-made the target and also the PVD condition. Then we can obtain different type of material in physics. Okay. Because if you have only 2 or 3 elements, it's possible to produce different type of different type of order.
Can we have one question from the remote Zoom? We have one from Shenzhen, from Professor Chen Furong.
Okay.
What is the technology barrier for precision? Goes down from 10 micron down to 1 micron.
Okay. In fact, even today, it's possible. Okay. In fact, technology barrier is a combination of 3D printing and other technology that can have a very nice shape. So today we can reduce to several micron. I think with a high precision machine or more expensive machine, we will be able to produce 1 micron precision. Then after the sintering, of course, the shape is different. Control this to 1 micron is still a challenge.
Okay, we have one question from Professor Colin.
Can I ask about the biocompatibility of the magnesium alloy prostheses? I mean, excess magnesium can be toxic. Okay. Is there any possibility of magnesium being leached out of the alloy in the implant?
Okay. In fact, the alloy we've developed is with 3 elements: magnesium, zinc, and calcium. Okay. Then by adding the contents of oxide, we can control the dissolution speed. Okay, that can be lower than the that will be lower in the level of safety, quite high safety. So, because in fact we can regulate biodegradability. So we are doing. We have successfully done small animal tests, and we are doing larger animal tests. If it's successful, we will see if we allow us to go to the human test. But basically, the concept is this material can edit some other element. So first of all, these 3 primary materials are very biocompatible. Okay, magnesium, zinc, and calcium. Yeah.
Okay.
I noticed when you built a lot of your 2D materials out of, with 3D printing, you built them out of making one-dimensional patterns that you overlap into a two-dimensional lattice. That lattice itself introduces another structural length scale and another structural symmetry.
Yes.
Have you ever thought about how to exploit that symmetry and that extra length scale in terms of your properties? For example, how it couples with external fields.
Okay. Yeah. Thank you very much for this very interesting question. So, in fact, it's possible to paint, say, line by line, circle by circle, or different type because. I think it's a very for develop the architectural material. This is ideal tools. In future, we can imagine we have say 10 heads, then each doing something, then to build the architectural structure. Okay, so it's possible, and yeah, it's I think it's possible.
Okay, Jian, I have two questions.
Yeah.
So the first one is when you show the relatively complex engine structures,
Yeah.
then you mentioned you can basically print it, use a huge machine to print it, right?
Yeah.
Okay. But with the different materials. But then if you have different materials in that, for example, in the parts of the engine,
Yeah.
okay, then every material have a different coefficient of thermal expansion, right?
Yes. Yes.
So how are you going to address this
Okay.
during the operation then?
Okay, in fact, this is what we need to handle even today if you do the thermal barrier coating. Okay, in fact, it's several layers. You have a so-called intermediate layer. You have so all this is to reduce the residual stress inside of structure. Okay, for the functional material, it's the same. We just published a paper on the perovskite material, how to do the press train. That can change drastically the property and also the life for say the life, the duration of this material, because everything driven due to the thermal expansion coefficient. It's like chips. In Intel, they have 50 people working on this residual stress issue. They call thermal management. Okay, the thermal management is a very important issue. And for the mechanical system, we have developed different tools. Say 20 years ago, 1998, I led one project called ANSPED, European Network on Stress, Surface and Press Stress Engineering. So basically how to take into account or introduce important good residual stress in the structure to extend the life. So today, Airbus, from engine to the structure, everything is press stressed. It's like glass. Glass 100 years, it's very easy to broken. But today, we do the ion exchange treatment to introduce very high compressive residual stress on the surface. For this reason, today the glass for our smartphone can be very thin. Today it's 500 micron. Tomorrow will be 100 micron, and they even target 50 micron. So all this material use this press stress engineering can say extend the life or performance.
Okay, so my second question related to your last slide. Okay, you show the something you put in water and also in the alcohol. Okay, and seems like magic. Okay, something can fold it and also can curl and also can flat.
Yeah.
So what was the mechanism? Behind
mechanism is this is some structure, hydrophobic, different property with the material. So when you put the alcohol, then that squeeze the water out. Then when you put in the water, that structure absorbs the water. Of course, you can do the inverse, but so it's you combine a hydrophobic material with another material, then that form this.
So that's related to the last armor you are using, right?
Yeah, that's related to the two types of material we use because we combine two material. Okay, so one material is to absorb water, another is to absorb, say, alcohol.
What kind of alcohol?
No, it's ethanol.
But between ethanol and the water, they are actually quite.
No, we don't say. we put yeah. We put one recipient of water and another recipient of alcohol. So the water inside of the structure is quite minimum.
Okay, the president.
Yeah.
Your 4D printing, did you invent it or is that common terminology?
Yeah, I don't invent it 4D because other people produce the 4D. What we have invented is a 4D printing ceramics.
I see.
Okay.
So the 4D terminology.
It's not invented by me. It's invented by others.
I think the 4D terminology is misleading. According to Einstein, there's only 3D. So I think if you call it 3D, flexible 3D.
Yeah, but it's with another.
Is that common in your?
Yes.
People always
now
call
it's
4D?
become even more common. So we try to stop this. As I said, if you add it once another stimulus, so we call all this 4D. So that means the structure, 3D structure, can have a morphing figure.
But in our living world, there's no 4D. It's just there's no such thing.
Yeah.
Unless you want to play some magic game. I'm just wondering whether that's common.
You can say you can paint something with a magnetic property, and when they change the shape, they change the magnetic field around you. And so I think it's
even with magnetic field, it's 3D. It's not. The fourth dimension is the time. And it's,
the time is with time. Basically, with time, as Professor Yang will say, if you have a stress, you have a relaxation of the stress, then with time that changes.
But that's
the
not
shape.
time.
Huh?
That
Still
is not time.
force. Yeah.
Yeah. Actually, we have one question.
That's why you call
Yeah.
Follow president question. So do you have 5D or 6D printing?
No. Okay, as I said, we already stopped this 4D, 5D, whatever. We just say, okay, 4D means you have another stimulus to change the geometry. Okay? But if you have two stimulus, it's still 4D.
Okay. Remo? Yeah. Yeah.
Well, Professor Lu, very amazing invention. Yeah. So I would like to follow up with Alex's question. So if for this one,
Yeah.
so if I want the flower to curve up more, then what should I do?
You want biodegradable?
Curving.
Oh,
Yeah.
curving.
Because,
Okay, you just need to do with say more materials that have more heterogeneity. Okay.
so can you control this?
Yes,
yeah,
yes,
you can
yes,
control-
yes, yes.
I see.
So of course there are some limit. You cannot fold this like something, but it's possible. If you have articulation point, you can fold completely. Because this one is without articulation point. If you imagine you design some articulation point at the interface, then that can completely fold. If this point can change the shape or rotate.
Thank you.
We have another question from Professor Solasson from France. You mentioned young modules divided by 20 as theoretical limit.
Yeah.
What was it related to?
It's basically we say if we have a perfect material, okay, the strength is roughly between 10. The Young's modulus is between 10 to 20 times of the strength. Okay, but right now the real strength is much lower because you have dislocation that facilitate the motion of the dislocation. Then usually we have say 60 to 100. Young's modulus is 60 to 100 times of the strength due to the dislocation. Okay, and in our material, as we don't have dislocation because the grain size is smaller than the 10 nano, it's a 6 nano. Then for this reason, the structure has another failure mode, but without dislocation. For this reason, mechanical property can reach a very high level.
Okay, Professor Lu Yang. Thank you, Professor Lu, for introducing us such a big picture for 3D, 4D printing, which I think indeed it's a very important direction for mechanical engineering. But I still feel like there are, in order to make it really useful in real life, I believe there are still many fundamental materials problems inside. Especially, many of them are actually traditional problems, like in the metal solidification or polymer engineering.
Yeah.
Yeah. By the way, so here you described the PVD as one type of 2D printing,
Yeah.
which is quite creative. But it reminds me that Richard Feynman, the physicist, mentioned ideally, ultimately, if we can build up materials atom by atoms.
Yes.
It sounds like another, in your way, it's also kind of a 3D printing.
Yes.
So what do you think? What's the ultimate resolution limit for 3D printing? Because I believe to achieve
you mean
a balance.
thickness?
I mean, you said like 1 micron or
Yeah, but
nanometer.
if you use ALD, you can do not atom by atom, close to atom by atom.
Yeah, but I believe there must be some balance between
Yes.
the cost, the time, and also the printing
Yes.
efficiency.
Yes. So for this reason, PVD is quite a good process. You know, some people produce solar panel, not solar panel, flexible solar panel with PVD. So that means if the rate can be quite high. Okay. So today we work on different lightweight alloy. So tomorrow I do believe we can produce wind, at least for the small aircraft using this technology.
Okay, thank you. Okay, Dave?
Yeah. So I was interested in this question of the limitation on the rapid response. I know that you've looked previously in your previous life about bistable and multi-stable
Yes.
structures.
Yes.
Have you tried printing and actuating bistable and multi-stable structures at this length scale?
The answer is yes, but today I don't have enough time. So what we do is we can also have a thin metallic sheet material. Then we can introduce specific residual stress distribution that take multiple shape, so morphing structure. Okay. And today we have print using 3D printing the structure. Some are naturally bistable, but the passing force, the threshold is too low. So we can 3D print the structure using our technology to edit this bistable property. So I think very soon we will have underwater system, car,
Yeah, it just seems to me
and aircraft with different with the morphing property.
It just seems to me if you can print these multi-stable structures, then you should be able to get actuations at the speed of sound, very close to it.
I think it's possible to solve to kill the turbulence. Okay, it's really possible. So we need someone crazy like Elon Musk to work with us to succeed in this kind of adventure.
Okay, Alice?
Limit of your 3D printing. I think that when you use two photon absorbing material, right? Okay, and 3D printing as two photon absorbing material, you can get down to the nanometer range. Okay?
Yes.
Because the record published in Nature, okay, about the freestanding bowl, okay, it's only about few micron.
Yes.
with like a cow, right?
Yeah,
Okay, you can
yeah.
print it with the home. It's talking about few nanometer in resolution. You can
Yeah,
get it.
it's
yeah.
possible. With nanoscript, this kind of machine is possible. The problem is the productivity.
Yeah.
Okay, because my field is a structure material. So I try to work on nano, but that should be applied for meter size component. Yeah, it's possible. We also work on this, so nanoscale structure printing, but as a result, it's not yet published. So what I can say is using this technology combined with super nano, because super nano, the smallest layer can be several nano. Then you have a very complex, super strong metallic structure.
Okay. Any question from your Professor CTU?
So for this picture, right, you call 3D printing actually is really simple heat treatment material, right? And by heaping by smart.
No.
You don't have to-
Smart is
Smart is treatment, right?
no, it's not heat treatment. It's a mechanical treatment.
Right. Well, it's treatment. It's a treatment.
Yeah, it's this one.
We just heat called metallic material heat treatment, not called 3D printing.
No. Sorry. This material is with 3D printing. Okay, so today, if you 3D print aerospace component, the major problem is fatigue. Okay, so this start to solve the problem of fatigue of 3D printed titanium alloy. But of course, this is a material study. It's not it's a 3D printed.
3D printing only control the shape, right?
Yeah. But
That's
fatigue sample, you cannot do directly the sample itself. So if I do a complex shape, when I compare, the people say, oh, what's the results for the standard fatigue test? So this one is a standard fatigue sample using the 3D printing plus heat plus SMAT. Then we compare with ASTM procedure, what is the fatigue strength enhancement? So the target is to show, of course, next step can be the real component to see personally, I think the real component, the fatigue life will be even higher because real component you have stress concentration, okay? Then it's even more sensitive, the 3D printing component is even more sensitive to the stress concentration. And using our treatment, we can put a compressive residual stress that can drastically enhance the fatigue resistance.
Okay. Any other question? This side? No? Oh, punching? Yeah.
Reduce the limit, the resolution. So eventually it's possible to print, the IC circuits in chips, right?
Yeah, I think the major problem is productivity. And also the high precision. Today with other lithography technology, you can go to 2, 3, 5 nano. And this is more difficult because etching is easier. Edit is more difficult than etching. Etching, you just say reduce with a very small speed, then you have your structure. But probably it's possible, but not economically valid. Yeah.
Okay. We have some other questions, but it's similar to what we have asked. So probably we can stop here because.
Okay.